Dear students, we are going to start the first video of Chapter 3, Basic Principles of Turbomachinery Flows. The outline of this chapter includes the definitional elements of the turbomachines, the energy transfer in the impeller, reaching Euler equation, the energetic evaluation in a turbomachine, then details on the performance curve, also the power versus flow rate curve, the discussion on the energy losses for the turbo machines with the efficiency curve, and the final performance curves that we obtain after all this inclusion. Finally, talk about systems, and then a last part of the chapter about similitude in turbo machinery flows. I hope we can do all the chapter 3 in 3 videos, but we will see. Turbo machine, as we have defined already for the global fluid machinery, it's a system to produce the energetic interchange between a given fluid and a rotating shaft. Well, I said there, find other definition if you can, improve it or comment on this. The thing is that the particular feature of a turbo machine in comparison with the other fluid machinery is that the interchange is done using a set of a blade or a set of blades, and typically this will be a row, and then we will have the definition of the stages that we have introduced on chapter 1. The difference between these kind of machines and the positive displacement ones that we have been studying on chapter 2 is that here the interchange is in a continuous way, not as it was previously for the fluid for the positive displacement machines. The flow rate here is not fixed and depends on the system where the machine is installed. We will see this difference, and it promotes quite important features. They are able to deliver much bigger flows than the positive displacement machine, and the maximum working pressure is quite limited by the operation of the machine. We have already discussed all these items also on chapter 2. The energy interchange is produced, as I said, by a set of blades, rows, rings, as we will see in the nomenclature. They can be diffusers, guide vanes, or distributors. If they are static, not rotating, or if they are rotating, they are typically called rotor or impeller. And some recovery elements as the volute and casing. To have an idea of what I'm talking about, we have some examples here. Impeller axial flow fan is axial because we have flow entering in one direction parallel to the shaft and leaving the machine also parallel to the shaft. Here we can see the detail of the electrical motor to move the fan. It can be a centrifugal pump like this one, and the difference between the axial geometries and the centrifugal one is because we have a 90-degree change in the flow direction. Here is zero change, global change, and here is 90 degrees because flow in this case enters like this in the direction of the shaft, and it leaves the machine as 90 degrees from this direction, perpendicular to this direction. An impeller, again a centrifugal kind of machine for a compressor, or we can see here the detail of the guiding vanes of an axial flow fan. So more or less the same as this one, but with some guiding vanes at the inlet. On the hydraulic machinery, we have the three main machines: Pelton, Francis, and Kaplan. We have here a picture of the two first ones: Pelton, the caps of the rotating hydraulic turbine, and also here the distributor of Francis turbine and the shaft, the main shaft here. At a smaller scale, a centrifugal compressor here, we see, well, these machines are quite big. The diameter here could be around 2 to 3 meters, and these ones are of the order of centimeters. So we also have a wide range of sizes for this kind of machines. And going to the energy transfer, trying to discuss and to reach Euler equation, we will start with the control volume at a given machine with some inlet mass flow and outlet mass flow, and some possible heat entering the system, and then some possible power being delivered to the shaft or interchanged with the shaft, some mechanical power here, right? And the typical discussion on the control volume, which would be a fixed one here, and we will see the details later on. So we have some fluid passing, entering and leaving the control volume. We go to the mass conservation equation. You will remember derivation of variation of mass with time as two terms: the variation over time of the mass inside the control volume, so integral of the density times differential of the volume, and plus the let's say the control surface effect, so the effect of the mass flow through the boundaries of the control volume, and this is done in a closed integral or surface integral of the covering the control surface, density times relative velocity times differential of the surface. For incompressible application, and if the control volume is fixed, as is the case here, without energy interchange, so without heat exchange of the machine, we have the classical mass flow conservation, mass flow in 1 equal to mass flow in 2. And if we consider that we don't have this density variation, we can remove density and we are left with the more classical equation for incompressible flow, which is Q1 equal to Q2. Going to the momentum or angular momentum equations, you have both them here with the external forces of the external torque. The equations are more or less the same. Variation over time inside the control volume of the variable, in this case for the momentum conservation, is the velocity times differential of the volume. And angular momentum, we have vectorial product of the position times the velocity inside the control volume, and then the surface integral for the control surface, in both cases again considering the main variable velocity or position times velocity, and the term for the flow, which is relative velocity times differential of the surface. If we consider these hypotheses, which are the classical ones for this kind of applications, so incompressible, ideal, and steady flow, so fixed, also fixed control volume, so we don't have this variation inside the control volume over time, and only forces or torque due to the shaft effect. Again, these hypotheses include that we don't have any thermal effect on the system, and if we are left with the 1D model, so we have only one component for the velocity or for the product of the position times the velocity and the relative velocity, and we consider them uniform. You see many variables, but in order to be able to simplify the study and be able to reach some conclusions, we can have a closer loop of our control volume. It would be like this. This is the global machine from 1 to 2, blades sitting here and rotating probably in a shaft direction like this one. And we start with a differential control volume like this one. So in fact, we have to go to do the integrals from for the blade height. We have blade height here from hub is the intersection over the blade span towards the tip or shroud, as is mentioned here. And to do so, we have this important equation that we are going to use, which tells us that the absolute velocity can be defined as a vectorial sum. This is a sum of vectors considering relative velocity, which is this W1, typically in the books, W1, relative to the blades. And this one is called peripheral velocity, is the velocity due to the rotation of the blades. So it's defined as omega times or vectorial product R, omega R in modulus, and omega vectorial product with the position. And this important equation is going to be plugged in the equations that we have. And in fact, if we take the second equation, the equation with the conservation of the angular momentum, we have something like this: only one external torque, which we can call torque of the shaft. And therefore, and then also because we don't have the variation over time on the control volume, we are left only with the control surfaces. And in this case, as far as we have 1D model and uniform flow, the other two hypotheses that we have included, we can extend our differential control volume to, let's say, average 1. And we have only one velocity at the inlet and another velocity at the outlet. In fact, due to the effect that we have, as shown before, this vectorial sum, we don't have a vector, but we have what is called a triangle, vector triangle, because this sum at the end is a kind of a triangle. It resembles a triangle in the vectorial shape. So we have what is called the velocity triangles at the inlet and the velocity triangle at the outlet. And only the terms also, the integral at the control surface is left only with two values, inlet 1 and outlet 2, for instance. And we can go developing these terms, and this is done in many books, and it's simplified here. We do the integral as mentioned between hub and tip, and the vectors, the vectorial products are obtained here. In fact, the vectorial product of the position times the velocity gives us a term here on the speed, which is called Vu, and it's the projection of V on the direction of U. So the projection of in the velocity triangles of the absolute velocity on the peripheral velocity. And so we get to this equation, plugging the mass flow, which is in fact the first approach to what is called Euler equation, and which we will use extensively, and which tells us the energetic interchange in this kind of machines with the hypothesis, with the whole set of hypotheses: incompressible, steady, uniform flow, only 1D, everything it's included here. And we reach this torque of the shaft is equal to mass flow times R2, so radius into average radius into, in fact, times this projection of V on U at section 2 minus R1 V again projected on U in section 1. And this operating with this and making it the torque as specific as a function of the mass flow. So dividing over the mass flow and multiplying the torque by the rotating speed, we get to a kind of a specific power, and the specific power gives us this equation: U2 times VU2 minus U1 times VU1. And this starts to be more in the shape of the classical Euler equation, as we can access in any book. We have here a summary of what we have been doing, and we will continue on this slide for the second video.